Hi, my name is Amy Sullivan, and I'm the current Vice President of AAAR. It's my pleasure to welcome you to the 25th in our monthly AS&T lecture series. This is a new initiative being supported by the Freelander Memorial Fund. With these lectures, we hope to highlight the amazing research happening in our community, tie our journal to other activities, and also give us the opportunity to come together outside of the annual conference. So each month, the editors of AS&T pick a high-impact paper to be presented by its authors. These lectures are being recorded, and they will be posted later to AAAR's YouTube channel, which you can access from the AAAR website under the Events tab. In addition, these lectures are being hosted by one of our student chapters. So I want to thank everyone who is helping to make all of these possible and all of you for joining us. And with that, I'll turn it over to our student chapter from the University of Arizona. Thanks.
Hello, good morning. My name is Jenny Lorenzo. I'm one of the members of the student chapter in the University of Arizona, and I have the pleasure of introducing our speakers. So Andrea Ferreo is a Clarkson University professor of civil and environmental engineering, the Clarkson Institute for Sustainable Environment Associate Director for Research. She's also a CARES faculty affiliate and an AAR fellow. So indoor air quality and aerosol exposure are her specialties. And for over 20 years, she has measured and modeled particle adhesion, detachment, and transport at multiple scales and quantified human exposure to resuspended particles in various exposure scenarios. Recently, she has studied respiratory aerosol emissions and their determinants. She has worked with communities, schools, and hospitals to monitor, analyze, and reduce aerosol exposure. So our other speaker is Mahender Singh Rawat, a fourth-year Ph.D. student at Clarkson University and studies respiratory aerosol emissions and their causes. His work is on viral resuspension from human activities and shows interest in indoor airborne particle exposure. Mahender is a graduate student organization leader and has published 4 research articles and a book chapter showing his dedication to this field. Mahender also enjoys outdoor photography, skiing, hiking, fishing, and kayaking outside of academia. I'd like to let you guys know that you can drop your questions in the chat box and we can read them after the talk. So without further ado, Dr. Farrow and Mahender, you can start the talk.
Okay. Thank you, Jenny, and thank you to the University of Arizona chapter for hosting us. We're excited to be able to talk about this this article from AS&T. I remember when Amy Sullivan introduced this idea to the board of directors at AAAR, and we were all super excited about it, and I didn't imagine I would be one of the speakers. So Mahender and I are super excited. Also, Amy gets a prize from this as well, which is she gets to be the next president of AAAR because of this and many other amazing ideas she has come up with over the years. So anyway, it's great to be here, and thank you for having us. Next slide. So Mahender and I would like to acknowledge our co-authors for this paper. Byron Erath is a professor at Clarkson in mechanical and aerospace engineering. His specialty is the aerodynamics of voiced speech, so he's an excellent collaborator for this work. And his PhD students, Tanvir Ahmed, who wrote the first paper that we wrote in this area, and Maytap Agirsoy. Also, we have Shimona Mandal, who's a statistician in the Department of Mathematics at Clarkson, and her PhD student, Danushani Sanaratna. I always mess this up, Sanaratna. So, and Dinu has already graduated and is a professor now. So, next slide. Oh, I just also wanted to mention, can you go back one, Mahender? Thank you. That the work was funded by the National Science Foundation and also an internal funding from Clarkson. Interestingly, we had proposed this work, something very similar before COVID hit, with our focus on influenza transmission. And so we sort of had our our team together and our ideas together when we submitted soon after COVID hit for the NSF grant. Another interesting point is pretty much what we proposed for the aerosol quantification and experiments was published a month later after we got the funding by Bill Ristenpart and Tony Wexler's group, the Seema Asadi's the first author paper. So doing pretty much what we had proposed to do. So we decided, okay, let's pivot. We're going to be looking at something a little bit different. And the other part of that work was on the fluid dynamics of the voice speech. So that was quite interesting, and it has resulted in this work. Okay, next slide. Another exciting thing about this is the work was selected as an ASNT vignette. So there's a 2-minute video on the concepts, the findings of the article that's for a general audience. So you can find that on the ASNT website or also the AAAR website. Next slide. So let's talk a little bit about the formation of aerosols and droplets in the respiratory system. So this slide is from Wang et al., the Science publication in 2021, where they're making a good point about separating aerosols from droplets. And droplets in this case would be the particles that are formed that are greater than 100 microns and would act more as projectiles, where the aerosols are smaller than 100 microns and would then be in the air for longer, could be in the air for minutes or even hours, depending on their size and what's happening in the room. So these are formed throughout the respiratory system. We have the respiratory tract lining fluid, and it's different in different parts. It's thinner, more like a surfactant in the lower respiratory region, and the alveolar and bronchial region, a little bit thicker in the laryngeal and oral regions, right? So we have formation in the alveolar and bronchial region from the, we're missing the presentation, Mahender. Could you share again? Great, thank you. So anyway, so we have the contraction and expansion of the alveolar and bronchioles, which result in this formation of the particle with the fluid film bursts. And then in the laryngeal region, we have spume formation and droplet formation from that. Also, the vocal folds are vibrating in the laryngeal region, which contributes to the formation. And in the oral region, we have larger droplets that are formed from the voiced speech. So fricatives and plosives and that are normal in our speech result in these larger particles that are the droplets that are formed. Next slide. Thank you. So also from the same publication, the authors talk about the 3 phases of the airborne transmission. So the generation and exhalation for phase 1, the transport for phase 2, and phase 3 is the inhalation and the deposition and infection in the respiratory system. So there's research in all of these areas. Of this work, of course, focuses on phase 1, the generation of the aerosol and the size distribution of the exhaled aerosols. So yeah, that's where we're focused, but not on the virus that is in the aerosol. Next slide. So just to dive in a little bit more on the aerosol size distribution based on sort of the mode that it was generated. And this is work from Johnson et al. In 2011, where the experimental results and then modeling separated the different modes, the B mode being the bronchial mode. And you can see that This is the smaller mode. So in the two size distribution plots, I realize you can't see my cursor because I'm not the one sharing, but so on the left-hand side, you see the speaking and coughing. So speaking on the top, coughing on the left. The size distributions look fairly similar. The bronchial mode is the mode that has is at about 1 micron and is a little bit tighter. Then the laryngeal mode would be the dashed line that's a little bit wider, and the oral mode, larger particles, where the mode is about 100 microns. So that would be the oral mode. Next slide. So two main factors for expiratory particle size distribution and for the emissions. Actually, the distributions look fairly similar with these two factors, but the emission rate and the concentrations increase both with loudness and with frequency. So the plot on the left shows you the size distribution from, this is actually our first publication in this area, Ahmed et al. It shows you the size distribution for different frequencies of people singing ah, an open vowel. So this is from C3 to C5 on the keyboard. For reference, C4 is middle C. So this is 2 octaves. That's in the range of most singers, or even non-singers, people who are singing. And so you can see that the higher concentrations, the size distribution shows that we're getting more particle emissions from the higher frequencies than the lower frequencies, and it's pretty consistent across the different participants. And then on the right-hand side, this is a plot from Gregson et al. And you can see from Jonathan Reed's group, and you can see that shows singing and speaking at very loud 90 to 100 decibels, and singing and speaking in the red. Singing is the boxes that are filled, and then the speaking is the circles that are lighter, a little bit softer, so 70 to 80. That's still, that's sort of normal speech. The singing and speaking at the 90 to 100 is very loud. And breathing as well. And so similarly here, you see that with an increase in the loudness, we get an increase in particle concentrations. Okay, next slide. So our motivation for this work is at the time that we were doing it, by this point, there were a number of groups who had produced results for respiratory aerosol emissions from the adult population. And as I showed you in the last slide, these were reported as a function of both loudness and frequency, also different vowels, fricatives, so different vocalizations characterizing those. But there had only been one study at that time. Now there have been a few. Fleischer et al. 2022 reported aerosol emissions for prepubescent children. And so we felt like this was an important age group to focus on, given our open questions about transmission and emissions, in locations such as schools and daycares. So also many of the studies that looked at sort of this open vowel or singing versus speaking had semi-professional or professional singers as participants. So we wanted to look at more general population. And again, we felt like this age-based emission data were needed for this health risk decision-making. Okay, next slide. So our main research question, how does age influence particle production? And so in order to look at that and evaluate for prepubescent children, sort of older children and adults, we looked at 3 different age groups, and you can see those age groups here. And Mahender will go into the protocol a little bit more. The important point, though, is that children are not small adults. We don't take the adult respiratory system and just sort of shrink it for the children, that the respiratory system is in development the laryngeal region, the pulmonary region, and especially from pre-pubescent to pubescent, there are changes in that system that could result in differences in particle generation. So next slide. So our hypothesis is that particle production increases with age during childhood, and there was some indication again from the Fleischer et al. Study that this is true, and that the pulmonary and laryngeal development of the children would have significant influence on the respiratory particle emissions. So next slide. I'm going to turn this right over to Mahender to talk about the experimental methods and results.
Thank you, Professor. So let's talk about the experimental setup. As you can see on the left-hand side, there's a person speaking in this image is depicting a diagrammatical picture of a person phonating in the funnel during the time of experiment. The funnel is connecting with the tubing with the APS, and let's talk about the different kind of instrument that we use to do this experiment. So the first one is the SPL meter. The SPL meter here used to measure the loudness in decibels. The second, we have conducted all the experiment under the laminar curve. The reason is to ensure that there is the background concentration becomes zero or negligible, so that we can only record the number of particles generated during the time of phonation. Next, we have the audio recorder. The audio recorder is used to record the audio files during the phonation, so that we further use those raw data files to analyze the relationship between frequency and loudness as compared to particle emission rate. Next up, we have the funnel. The funnel is the place where the participant need to come and do all the phonation activities. Then APS, aerodynamic particle sizer. I'm sure like you must have aware about this term, but this is to make sure that the recording of particle concentration and aerodynamic particle sizer during the experiment. Then this thing is connected with the computer, where we record the data and also set up all our experimental run. Now, let's talk about the experimental procedure. As Professor Farooq has already mentioned, we have 50 participants, and we further divided into 3 different age categories. The first age category called as Phi1, which consists of 6 to 11 years of 8 girls and 6 boys. The second age category is Phi2 of 12 to 18 years, consisting of 10 girls and 12 boys. And the third age category is all the adults above 18 years, consisting of 6 female and 8 males. So all these participants are later asked to perform similar kind of experiment. And the first experiment was to produce a sustained vowel A at a specific frequency of 262 Hertz. That is our baseline phonation. So this experiment is performed in such a way, we ask the participant to phonate for 5 seconds, like followed by the 10 seconds of comfortable breathing. Next, we ask the participant to do the repeat annotation of PA, activating the oral mode at the same frequency of 262 Hertz. Here, each annotation of PA is representing a 1 second interval, just like PA, 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 and a whole duration of 5 seconds of phonation, followed by the 10 seconds of breathing. Next, we ask the participant to take a deep breath and do a sustained vowel A, to activating the bronchial mode at the same frequency of 262 Hertz. And the participants perform this experiment in such a way, they take a deep breath and then do just immediately after taking the deep breath. And this experiment is also recorded for 6 times. Also, to make sure that we are following the same frequency and amplitude, we used an online piano and a metronome, so that we can able to control the range of the frequency during the time of experiment. Also, we ask the participant to do singing and speaking happy birthday at a comfortable loudness and pace. This experiment is further repeated for 2 times, followed by the last set of experiment where we ask the participant to breathe at a comfortable rate for 30 seconds. Okay. Let's talk about the data analysis part. So we collected the raw data using the APS and the microphone. We further divided into 2 different segments. One segment, we collected the raw file extracted from the microphone, and we performed the statistical analysis, where we look for the correlation between the particle emission rate with loudness and frequency. Although during this experiment, we controlled for both of these parameters so that we support our main hypothesis, which is the age progression effect on the particle emission rate. For that, we use the raw file extracted from the APS, and we further divided into two segments. One is the size distribution, which we use the particle concentration to plot all the different particle sizes for different vocal exercises and different age groups. Then we accounted for particles per second. So the approach of our method here is to account for each and every particle which is generating during the phonation. To do that, we did a calculation where we count for total particle number generating during that 5 seconds of phonation plus the 10 seconds of comfortable breathing, because there is a delay in the instrument so that we want to collect all the particle which is generating during that 5 seconds, and that we further divided by the 5 seconds of phonation time, which is actually the emission rate. Then to account for total particle emissions, we did the particles per second times the total flow rate, where the flow rate is 1 liters per minute for the sampling and the 4 liters per minute for the sheet. That divided by 1 liter per minute for the sampling flow rate. And that's how we account for total particle emission rate during that phonation. Then we further did the statistical comparison for emission rates for different age groups and vocal exercises. Okay, this slide is showing that how these three different variables affect the particle emission rate. So here we have three different variables: amplitude, age, and frequency. We compute that the relative importance for the particle emission rate. For that, we performed a relative importance with the multiple linear regression model and found out that the highest contributor here is from the age with 94%, and amplitude and frequency affecting very minimal by 0.5 and 1%, which is our main hypothesis that all our results are being affected only by the age progression. Okay, here we use the box plot and the violin plot. We have three different age group category for the vocal activity and vocal intensity. And for that, as you can see, for the first age group, we see a slight increase for the adult age. This is because of the post-puberty changes and the voice modulation for the adults, which tend to generate a little bit higher as compared to our first two age groups. Although when we compared the vocal frequency among the different age groups, we found out that the smaller kids are having a slightly higher frequency than our desired, which is 262. And the reason is that it is very hard with the kids to keep on maintaining the same frequency, which we are asking to do during the time of the experiment. So with this, we show that there is a little variation, but that variation is not significant. That impacted our result for the particle change, which was impacted by the age progression. Next up, we have here in this plot, we show the violin plot and the box plot for different age groups across different activity. And we used a median value to show the difference between each vocal activity and each age group. As we compare deep breath from the first age group to second and to the third, we see an increase in trend from the each age group, and this is what we hypothesize. Also, if we compare the other two activities such as normal and repeated we found out the similar trend with increase in age progression. Also, it is interesting to note that there is also some kind of pattern which is following between these different vocal exercises, which we further analyze using the constraint inference plot. Next, we cluster all the three previous shown activities and turned as a group phonation. So here we compared the group phonation with singing and speaking happy birthday. Also, when we compared these specifically individual group phonations across the three different ages, we found out that there is an increasing trend again following the same pattern as we move from the first age group to the second and from there to the third. Also, we found the similar pattern reported by other study where they found out singing tend to generate higher particles emission as compared to speaking. Also, this may be a reason due to there are pauses between the speaking. That's why the speaking tend to generate less number of particles as compared to the group phonation and singing, where we have a continuous speech going on. Okay, so as I mentioned earlier, As I mentioned earlier, we saw a different kind of trends among different activities. So here we would like to compare our different activity, that what are the trends we are getting here. So for that, we did a constraint inference analysis where we compared deep breath R to normal R and repeated R. So as we can see that we found a decrease in trend for the first two age group, where we see deep breath R reported to be having a higher particle emission rate comparing to the repeated PAR, although that trend was not seen among the adult age group, although we saw a different trend, which is called an umbrella trend, but an overall pattern of decreasing trend from deep breath R to normal R was repeated there, which is statistically significant also. Next, we compared the same scenario where we grouped all the three different vocal activities such as repeated PAR, normal R, and deep breath R, and we compared it with singing and speaking. So an overall decreasing trend found out between speaking from speaking to group phonation, and that trend was also statistically significant across all three age groups, apart from the first one where the first group phonation and singing showed decrease in trend, but that trend was not statistically significant. Next, we use the particle concentration to plot the particle size distribution here. And we found out that, as we reported earlier in our other results, that deep breath and singing tend to produce tend to generate higher particle concentration as compared to the other activity. Also, we found out that there is a similar mode were identified for all the age groups, with the primary mode being seen at a median diameter of around 0.6 micron and a secondary mode seeing around 2 micron. These results are consistent with the other published studies as well. To further investigate about these two different modes, we did a fitted bimodal log normal distribution. Here, this result is specifically showing for the 6 to 11 years age group, where we fitted this bimodal log normal distribution to find out those two different modes, which we called as the primary mode and the secondary mode. And when we further analyze for all the different age group across all the activity, we computed a table where we found out a trend, which is the primary mode tend to be increased with the increase in the age groups. And also we found out a decrease in trend of secondary mode, which is going from the adult to the second age group of 12 to 18, and the highest found in 6 to 11 years age group. Okay, with this, we also look for the statistical outliers, so which are called as superemitters. So what statistical outlier is? These are the participants in our study which tend to generate the particle at a much higher rate as compared to the normal study population. Here, we look for two different type of outlier. One is called the mild outlier, and the second one is called the extreme outliers. The mild outliers are basically the upper 1.5 times the interquartile region, whereas the extreme outliers are 3 times higher than the interquartile region. And for that, we found out an extreme outlier of M15 across the 6 to 11 years age category. We found no extreme outliers for 12 to 18, although we found 2 outliers such as M2 and F4 for the adult categories. Now, we further compared our study with some of the published study, so to know about what kind of pattern is seeing there with the other study when we are comparing our study. So in our study, I just quickly go through it. Since I already mentioned all this thing, we did group phonation, normal R, repeated PAR, deep breath R, singing and speaking. We recruited 50 participants with 3 different age groups, and we found out that the adults are generating 2.3 times higher particle as compared to 12 to 18 years old, and 4.7 times higher than the 6 to 11 year old. Whereas Bagheri reported for different activities such as speaking, and they recruited 132 participants for the age category of 5 to 9 years and 10 to 14 years. And they reported for the concentration. So they found out that the concentration would increase with the age among these two age categories. And they also reported that a cumulative volume of PM 2.5 is 2 to 8 times higher than the adults. Similarly, Archer et al. Also looked for the different activities, such as speaking at a control and controlled sound pressure level, where they recruited 136 participants, and they recruited 2 different age categories, 12 to 14, which is following our 5-2, and the adults, which is following our adult category. And they found out that the median particles per second for the first age category reported for 40.7, whereas the median particle emission rate reported for adult was 60.1. So they do see an increase in trend, which is just 50%, whereas we reported a 200% increase between the two different age categories. Also, Fletcher et al. Looked for the different activities such as breathing, speaking, singing, where they recruited 30 participants, 15 pre-adolescent and 15 adult subjects. So they found out that with breathing, speaking, and singing, the children tend to generate lower particles, and the particle emission rate increased by a factor of 4.3 for adult versus children across all different conditions. So the recent paper published by Tracy, where they look for speaking, and I must say they have the highest number of recruitment for the kids, where they look for 371 children across 6 to 12 years, and they found out a median emission rate of 25.6 particles per second. And while loudly speaking, they found out a median emission rate of 40.6 particles per second. Although it is interesting to note that they didn't find any age-related difference that was reported among the 6 to 12 years, although we found an age-related difference as we progress from one age group to the other. With this, I would like to conclude my study. So the median emission rate for adult was 2.3 times higher than the 12 to 18 years of age group, and then 4.7 times higher than the 6 to 11 year age group for the all three vocal tests. We also found a decrease in trend from deep breath R to normal R to repeated PA for all the age categories. The particle emission, the particle number size distribution have a primary mode reported for around 6 micron called as bronchial mode, and a secondary mode reported around 2 micron called as laryngeal mode, with children having a smaller primary mode and a larger secondary mode as compared to adults. So the result from this and the similar study can be used to better predict an infectious droplet emission and spread in different indoor environment such as school. With this, thank you for your time and listening, and we are happy to take your questions.
Thank you, Mahender and Andrea. Thank you so much for the wonderful talk. It was really insightful and engaging. And yeah, I have some questions here. And the first question is from Ria, and it's on about your question. It's about slide 11 to 12, which she says, will some particles be lost while traveling through the bent pipe from funnel mouth to the aerosol-based collector? That's the first question. So I don't know if you want to answer that.
Thank you, Ria. Yes, we calculated the particle losses. They were minor. This is consistent also with calculations done by the Asadi et al. Publication. So less than 5% losses in that. The tubing's pretty large. We did have some losses in the funnel, however, which is talked about in the discussion of the paper. For the adults, where they had their exhalation rate was higher, not all of that exhalation made it into the instrument. So we did calculate some losses there. If anything, that would increase the difference, since the losses would be more for the high flow rate exhalations. So it would make the differences between the adults and the children's a little bit larger. So anyway, that's methods improvement that's in the works.
Okay, thank you. Another question, it says, did you care for background particle concentration? This is a question from Carl, and it's about your slide 12. Did you care about background particle concentration?
Why don't you take that, Mahender?
Yes, we do consider about the background particle emission concentration, because that's why we perform all the experiment under the laminar hood, and we make sure before we are coming to perform the experiment, we keep the laminar hood on so that we can record a 0 background concentration, and then that's where we start our experiment.
Thank you. We also have a question that says, based on slide 14, she says, based on which property of the instrument, the concentration and size distribution is measured. Also, yeah, aerosols are in form of water droplets, right?
So I can take that one. So we're using the aerodynamic particle sizers, which accelerates the particle and measures the time that it, from one location to the next. So this is, the property is based on that. So it's there's also an optical measurement within the aerodynamic particle sizer, but we're using the range where it's the aerodynamic properties. So that's the is it water? There's a lot of water in it. This is respiratory fluid, right? So it's the respiratory tract lining fluid, which has some protein, salt, it's not just water, but there's a lot of water.
Thank you. And another question is based on slide 17. Ria was saying, what is meant by n equals to 14, n equals to 12?
Yeah.
Maybe if you can recap that.
Yeah, so those n are basically the number of participants. So we initially describe it in the first few slides here. Let me go through it. So if we come to this one, so n is basically like the sum of the girls and boys in the first age category, which is 14, and the sum of the girls and boys in the second age category, which is 22, and the sum of the female and male in the third age category, which is 40. I hope that answers.
Thank you.
It's a good question though, because depending on the analysis that we're showing you, we used, because for each vocal exercise, they were repeated 6 times. So each individual vocal exercise was included in the analysis for the violin plots that Mahender showed. But for the analysis that was on the slide, I think it's 17, those 6 values for one individual were combined. So good question. The N there was the number of participants.
Another question is, what's the average particle size measured? It's a question from David.
Average particle size.
Probably the best thing to do is to look at the size distributions there, right? So we're seeing the biggest mode, the primary mode, at about 0.6 microns, right? And then the secondary mode is larger at about 2 microns. So you can see the other thing that's important here is that depending on the vocal, depending on the exercise, some of these, maybe go to the next slide, Mahender, for the children. As we mentioned, the primary mode appeared to be smaller for the children for a few of these exercises. So if you see, well, for all of them. So, and the primary mode looks like it's below 0.5, which is the lower end of what we can measure for the size distribution using the APS. So I would say that because we needed the modeling extrapolated, we're going to need, this requires a little bit of further study to see if this finding is true. With the shift in the size distribution for the children compared to the young children compared to the older children compared to the adults.
Thank you for that, Andrea. Another question is, did you investigate the effect of age during the various exercise? If age was treated as a numerical variable instead of maybe compared to like categorical? It's a question from William.
Wow, thank you. So there was only one exercise where we looked at age, and that was when we, Mahender, can you show the slide that has the difference, the contributions from age, loudness, and frequency? Yeah, here. So this modeling, we used age as a number, so we looked at all the ages separately, 1 year segments. For the other ones, we used a category.
All right, thank you. Also, there's a question from Ui. I don't know if I pronounced the name well. Sorry if I mispronounced it. Did you correct the size due to evaporation?
No.
Sorry, no, we didn't. By the time the aerosol gets to the APS, a lot of that has been, so we're measuring the particles as they're emitted from the mouth, but then also it takes a little bit of time to get to the APS. So the particles will have shrunk a little bit, but no, we didn't adjust them, the particle sizes.
Thank you. Also, you have a question from Carl. Says, do you have an explanation for the increasing aerosol emission correlating with the increasing loudness?
Yes. So if you look at how the aerosol is formed, especially so if we look at the two areas that might impact this the most, which would be the laryngeal region and also deeper in the respiratory tract, the alveolar bronchial region, you have, so the alveolar bronchial region, you have expansion and contraction, and you have the fluid film burst occurring. And this is dependent on to the amount of air that's moving through, right? And the fluid, and that interaction between the physical, between the aerodynamics and the physical, the fluid and the lining. So also in the laryngeal region, it's gonna change the flow rates basically, right? So if you can go from when your glottis is shut, you have a flow rate of 0, and you can move all the way up to say 40 meters per second for the flow moving through. So with louder singing or louder talking, you have higher flow rates, which would increase the formation.
All right, thank you. There's a question from David that says, do you guys use SMPS for your measurement?
No, we use just APS.
Good question, though. I think that, if you want to get at those smaller particles, especially since we're seeing the mode potentially below 0.5 for the children, it's a good addition.
Also, we have a question from Rio. It says, is there any physical reason behind the bimodal pattern? Can we infer any physiological reasons behind this?
You want to take that, Mahender?
I think yes, there is and it's mainly related to the prepubescent and postpubescent changes during the vocal cord formation, and that can lead to the two different modes of production as compared to the different age categories.
I think you could also look back at the Johnson et al. Paper slide that I showed that shows, your size distribution is going to shift based on where the particles are formed, and they're formed in multiple regions in the respiratory system. So you can see that the laryngeal mode has shifted a little bit to the right. The bronchial mode is the smallest mode.
Thank you. We have a question. It's also from Francisco, who says the evaporation is probably significant. So what you measured at the residue particles after evaporation of water in the original aerosol. Do you estimate this effect?
Yeah, this is a similar question to before. I think that the reaching equilibrium happens pretty quickly for these particles once we emit them into the air. And so there is some evaporation that occurs between when the aerosol is emitted from the person and it travels into the APS. That happens in a couple of seconds. So some of that shrinking has already occurred, a good amount of it. But again, we didn't account for that.
So I think I have one more question for you guys. So it says, I might miss this. Did you compare the bimodal pattern with BLO model? It's from Ewi. So did you compare the bimodal pattern with maybe the BLO model?
Yeah, I think if you look right here, so in this case, our bronchial mode was smaller. So this shows at about 1 micron. So I would say that our lowest mode you could equate to the bronchial mode here. and then the larger mode. It's there could be some bimodal emissions from formation of particles. Like for the laryngeal region, you would have different formations. You can have these strands or sheets of fluid that then break up. You have the vibration of the vocal fold. So this really, I think, could use more investigation into the formation mechanism and the associated size distributions. But yes, I think if you look at our results and this, the Johnson et al. Figures, you can see sort of the bronchial and the laryngeal modes in our data. You cannot see the oral mode because, again, we have 20 microns as the high end for the APS, so we're not measuring those particles.
Thank you so much, Andrea. Thank you, Mahender. It was really great learning about this amazing research, and I think it's something to kind of get into and also kind of get better to know some of these things that are happening, and it's wonderful. Thank you.
Thank you.
Well, we appreciate the opportunity to talk about this, and we're happy to answer questions if people have them later. See if anything else pops up here. We just see thank yous, but thank you to everyone for being here with us. And thanks for U of A for hosting.
It's a pleasure, always. Thank you. And I think I will hand over to Amy.
Yes. Well, thank you. That was a wonderful talk, and what a wonderful discussion following it. Thank you all for joining us, and please come back next month for our next one in the series.